The fanfare and the excitement are but dimly remembered now, though only a brief interval of time has elapsed since America's first space hero thundered skyward, riding in the capsule of a Mercury Redstone rocket. The date was January 31st, 1961, and from that moment on, history has been passing in high gear. But while new heroes are born every day, the nation still honors that bold pioneer who led the way in the best traditions of the great American frontiersman. Today, he basks in the glow of his memories amid the peaceful surroundings of the National Zoological Park in Washington, D.C. Astronaut Ham. Ah, fame, 'tis but a fleeting thing at best. Home to Ham, the space chimpanzee, was Holloman Air Force Base in the Tularosa Basin of New Mexico near Alamogordo. And more specifically, the section designated as the 65th 71st Aero-Medical Research Laboratory. Here, Ham was trained and conditioned for his history-making flight in much the same way our human astronauts are trained and conditioned. And here, some 200 of his fellow chimpanzees are taking part in a program designed to probe the limits of man's endurance. To predetermine how well man will be able to adapt to the strange new environments he will encounter as he ventures deeper and deeper into the vertical frontiers of sky and sea. Because these primates are so remarkably similar to man in mental as well as physical makeup, they are ideal surrogates for man in tests involving potentially hazardous conditions. The close comparison exists in bone and muscle structure, in blood types, in the composition and functioning of the body organs, and in the capability of responding to stimuli and solving problems. Thus, data obtained from the chimpanzee may be extrapolated to the performance of a man under comparable circumstances. But it was not always that simple. Back in the 1940s, the Aero-Medical Research Laboratory set out to learn the answers to some very formidable questions. The Earth was a familiar environment, but so-called outer space was full of new and unknown hazards. To gain more knowledge about the problems our astronauts would encounter, the upper atmosphere was first tested by a variety of stand-ins for the human space voyagers. At the White Sands Proving Ground, a missile test site not far from the laboratory's present location, mice and small monkeys rode out to the edge of space in captured German V-2 rockets. And later in the famed Aero-V rocket of U.S. design, to explore the wiles of weightlessness, acceleration, and cosmic radiation. As time went on, scientists of several countries sent up weird salvos of biological specimens, including radish seeds, fungus spores, grasshopper eggs, fruit flies, monkeys, mice, turtles, dogs, and cats. But despite the odd nature of their passenger lists, these men knew exactly what they were doing. Their investigations resulted in much useful knowledge. And at the Holloman Aero-Medical Laboratory, Air Force doctors were acquiring the answers to some of the enigmas that had puzzled men since the days of Archimedes, Newton, Copernicus, and Kepler. Much still had to be learned, however, and man himself took over the test role in a number of important studies. In Project Man High, Major David G. Simons proved that it was possible to survive and to perform certain necessary technical tasks while enclosed in the cramped confines of a sealed capsule for long periods of time. It fell to the lot of two other Air Force officers, John Paul Stapp and Eli Beeding, to demonstrate that men could withstand G-forces as they would be experienced during a rocket launch and re-entry. On the Holloman rocket sled, Stapp reached a top speed of 640 miles per hour and slammed to a full stop in 1.4 seconds. He suffered no serious or permanent ill effects from the 55G peak deceleration load he took. Beading subjected himself to an incredible 83 Gs in a later test made on the shorter Daisy track. Beading went into a state of shock and for a time was considered to be in a critical condition. 5 days later, however, he was back at work with no permanent disability. These and other intrepid human volunteers took risks at least as dangerous as those they had required of the animal subjects. And the data thus gained contributed significantly to the successful flights of Alan Shepard, John Glenn, and their successors. Over the years, the work of the Aero-Medical Research Laboratory has broadened and increased, becoming more and more sophisticated as we move deeper into new fields of science and space exploration.
With the successful completion of Project Mercury, the laboratory examined how it might best utilize its assets in meeting Air Force and Department of Defense goals. Our chimpanzee colony was fast becoming the world's largest. Our Daisy decelerator and the associated tools in the field of acceleration research were unique. The comparative psychology group had gained valuable experience working with spaceflight problems. With these assets, it seemed logical that we should specialize in the study of high-risk operational situations prior to exposing man to them. Animal surrogates would be used to obtain data that would be meaningful in evaluating the danger to man. And in addition, our chimpanzee colony was a resource of great value in medical research. Accordingly, we launched a program of experimental medicine that included a comprehensive study of heterotransplantation, simian and human blood groups, and infectious diseases. New blood groups have been discovered and genetic differences have been shown in human white blood cells and platelets. A detailed study of the functions of the primate brain is now underway. Our goal is to contribute substantially to the military medical mission by making man's journey into space a safer one, and at the same time, to aid in the advancement of human and veterinary medical research.
The chimpanzees are purchased from dealers who import them from the jungles of equatorial Africa, and frequently their physical condition is less than satisfactory. Their first experience is puzzling, but not unpleasant. They are given a thorough physical examination in the laboratory's immaculate, well-equipped veterinary facility. Here they are treated with the professional care accorded human patients in a modern hospital, and often gain their first insight into the basic kindness of their fellow primate, man. These facilities serve a multiple purpose. Care of the animals is fundamental, of course, but beyond this is the requirement for establishing physiological baseline data on each subject, so that normal functions may be compared with any changes occasioned by the tests it will undergo later. Detailed medical records enable the veterinary staff to maintain a close watch on the health of each animal. Nearly every branch of medical research is covered in the separate laboratories, providing a far-ranging capability in the study of physiological conditions. The basic and applied research programs, conducted with up-to-the-minute equipment by specialists in their various fields, are benefiting all our armed services and creating great interest among the leaders in experimental medicine and psychology, both in this country and abroad. The animal's diet is a prime consideration. Appetizing meals are prepared in the spotless kitchen. A specialty of the house is the chimp cocktail, a tasty and nutritious concoction of vitamins, pablum, milk, and flavored gelatin, and one that every red-blooded jungle boy considers a real treat. When the newcomer to the chimp colony has completed his physical examinations and become accustomed to the routine, he is ready to begin his experimental work. Now, as man's representative in the research program, he is trained on certain basic performance schedules, using equipment designed and developed by laboratory personnel, in which he responds to signals by pressing levers and pushing buttons. The learning process is aided by positive and negative reinforcement, by applying a mild electric shock to the soles of his feet, which causes some discomfort but no pain when he fails to give the proper responses, and by rewarding the animal with a food pellet or a drink of water when he performs correctly. The performance task sequences are programmed in advance using relay timing and switching circuits and electronic solid-state equipment which automatically control the presentation of the stimulus displays and the recording of the animal's responses. Each animal's performance in this complex work program, designed to approximate human tasks involving the major senses, motor behavior, and difficult discriminations, is carefully recorded and maintained in a personal record. In the days to come, our astronauts will be asked to attempt more and more hazardous feats, such as working at complicated tasks outside their capsules or space station. What would happen if an astronaut were subjected to a sudden loss of pressure within his spacesuit? To find the answer to this question, the laboratory has undertaken a series of experiments with trained chimpanzees. Object? To determine the behavioral, physiological, and pathological effects of decompressing test animals to a near vacuum of less than 2 millimeters of mercury pressure. 2 days before the test, the animal spends from 7 to 8 hours in the decompression chamber at ambient or ground level pressure. Restrained in a form-fitting couch with physiological sensors recording such functions as heart action, brain impulses, respiration, and skin temperature, the animal does his chores in an environment that closely simulates the actual experimental conditions. His responses are recorded, establishing basic performance data with which to compare the results of the test to follow. On the day of exposure, the subject is first given a physical examination and then placed in the chamber. After the instrumentation has been checked, the door is sealed and the animal is denitrogenated by breathing 100% oxygen for 3 hours. He performs the tasks for which he was trained, and the results are measured and recorded. 30 minutes before rapid decompression, the chamber pressure is gradually reduced to a simulated altitude of 35,000 feet, where again the animal's performance and physiological reactions are monitored. Full decompression is effected when this large tank, from which the air has been withdrawn, is open to the test chamber. In 0.8 of a second, the simulated altitude inside the chamber soars to 150,000 feet. For all practical purposes, the equivalent of outer space. The animal continues to respond for approximately 15 seconds, and then is no longer able to operate the performance panel. Slightly more than 2 minutes later, the chamber is recompressed to a pressure altitude of 35,000 feet with 100% oxygen. After 2 to 4 hours at this altitude, the animal is once again performing at his pre-decompression level. Tests made thus far indicate that the average duration of total impairment in which no behavior is observed is 35 minutes, while the average time until total behavioral recovery occurs is 2 hours and 20 minutes. At the end of the recovery period, the animal is removed from the chamber. He has survived the experiment in good health. In fact, continuing tests show that he is able to perform as well as he did prior to the exposure, and no delayed effects have been observed after as much as 1 year. This research has been highly rewarding and has added to our understanding of a serious hazard the astronauts of tomorrow may have to face. And somehow, one gets the impression that the chimpanzee is proud of his contribution. Another experiment of interest conducted jointly by the Aero-Medical Research Laboratory, where the animals are trained, and the Los Alamos Scientific Laboratory, where the actual experiment is conducted, involves a different primate subject, this time the rhesus monkey. Its purpose, to determine the degree to which a physiologically dangerous level of radiation exposure will affect the ability of space crews to perform their required tasks while in flight. Again, the animals have previously been trained to do certain tasks on a performance panel. Their relative ability to accomplish the same tasks while under exposure to varying degrees of radiation provides data that can be applied to the performance of a man under similar conditions. Each monkey spends 30 days before a display panel like this. seated in a restraint chair equipped with a spring-supported board that allows him to exercise his legs. The test day is divided into 4 6-hour periods. 2 a.m. to 8 a.m. is a work period. The next 6 hours are devoted to rest, followed by another work period from 2 p.m. until 8 p.m. 6 more hours of rest complete the daily schedule. For the first 10 days, the monkeys receive no radiation. The data collected during this time are used to establish accurate baselines against which possible effects of radiation can be compared. In the second 10-day portion of the experiment, a certified 80 Curie cobalt-60 source generates continuous gamma irradiation at the rate of 50 rads per day. The total dose of 500 rads received by the monkeys would be considered lethal in man if accumulated over a shorter period of time, say in several hours. 4 lithium fluoride dosimeters implanted just under the skin on the back and chest measure the exact amount of radiation each monkey receives. The final 10 days are used as a post-exposure work period to observe whether recovery or adverse delayed effects occur. Early results have indicated that 500 rads of gamma radiation delivered at the rate of 50 rads per day failed to degrade the performance of the test animals in either accuracy or reaction time. The inference is that man may be able to tolerate substantial amounts of radiation and still perform efficiently if the dosage is received over a sufficiently long period of time, a definite advantage in civil defense, military, and spaceflight operations. On the field of pure medical research, the laboratory is conducting an interesting study in immunohematology with the aim of adding to our knowledge of the blood groups in man. Using immunological techniques, the specialists in veterinary medicine are classifying and cataloging the fine differences in blood properties within the chimpanzee species, which share blood groups O and A with man. Their work is expected to be of great value to the medical community. These are only a few of the many research activities currently underway at the laboratory. Prominent among the remainder are such projects as a study of visual acuity and thermal injury to the eye, using the Landolt ring technique to establish visual parameters, and a highly significant series of experiments in neurophysiology, in which both simian and human subjects are used to establish data on the effects of altered environments. Programs entering the laboratory are frequently conducted for or in collaboration with a variety of outside agencies. Many universities have been involved, as well as every branch of our armed services. The Defense Atomic Support Agency, the National Aeronautics and Space Administration, the National Institute of Health, and other federal activities have shared in the work of the laboratory. But while the pathway to space may be lined with animal tracks, only man himself, in the final analysis, can determine exactly how far a man can go. Volunteers for human deceleration tests qualify on the small bopper sled. Powered by rubber cables, the bopper is capable of creating deceleration forces in the neighborhood of 20 Gs. The qualifying runs seldom exceed 10 Gs, however, and the men receive thorough physical examinations before and after each run. The bopper is also used for testing purposes with both animal and human riders. Graduates from the bopper may be called upon for more sophisticated experiments, such as a ride on the Daisy Track's omnidirectional sled. Designed to study the impact forces connected with a hard landing, for example, the Project Apollo capsule escape system, this sled permits testing with the subject facing in any desired direction and seated in almost any desired position. An advantage of the Daisy Track is the direct line instrumentation setup, a reliable and very accurate method of recording the test results. Information gained from these experiments will help in protecting the astronauts from physical impairment. The volunteer has taken part in a study of pulmonary functions before and after impact. The primary step is to establish baseline data on the subject, his maximum voluntary ventilation and pulmonary diffusion capacity, before he rides to a jolting halt on the daisy track. Impact or abrupt deceleration is an inevitable byproduct of increasing speed. The researchers are probing deeper and deeper into the human body to see what happens under these conditions. Is there a transient deformation of the lung that might impair, for instance, the efficiency of a lunar exploration team? Sensitive instruments in the hands of expert medical men and technicians are providing the answers to these and a host of other questions spawned by the space age.
2, 1, fire.
The dedicated scientists, the human volunteers and their animal partners of the Holloman Aero-Medical Research Laboratory are helping to shape tomorrow's way of life. And it seems a most natural thing. If animals share the earth with man, why not the universe?